So for the major topics, we talked about the Fermi-Dirac distribution function, and then we talked about how applying the Fermi-Dirac distribution function for electron gases. So the first student learning outcome is to describe the physical meaning and qualitative energy dependence of the Fermi-Dirac distribution function. So this is the equation for the Fermi-Dirac distribution function. Its meaning is that this function actually gives you the probability of a quantum state at energy E being occupied by an electron. Obviously, this probability does depend on the temperature of the system and also where your energy is with respect to the Fermi energy of the system. Since we have the Pauli exclusion principle, each of those quantum states can be occupied by no more than one electron. So this distribution function also gives you the average number of electrons on this quantum state. And based on this distribution function, you can draw it as shown in this graph for all the at zero temperature, all the state above the Fermi energy will have zero probability occupied by electrons, so no electrons in these energy levels. For energy levels below the Fermi energy, they are going to be occupied by 100% probability. All of those states are going to be filled. This is for zero temperature, and that means we have a step function. When you go to some finite temperature, this step function will be smoothed out a little bit, but this range of transition zone is only going to be happening within a few kT above or below the Fermi energy. At 3 kT above the Fermi energy, the probability goes down to 5%. 3 kT below the Fermi energy, it goes up to 95%, almost completely filled. So obviously, as you go to higher temperature, this transition range becomes wider, but overall, it's going to be a few kT above and below. So at room temperature, kT is only 26 millielectron volts. This happens within something like 100 millielectron volts or less within the Fermi energy, which is a relatively small number compared to the energy range of a particular band. The width of a band is going to be on the order of several EVs. So with that, you should also be able to calculate the probability of a quantum state occupied by electron, given the temperature, given the energy in reference to the Fermi energy. Applying this theory to free electron gas at 0 Kelvin, so the next outcome will be to derive the Fermi energy of the system at 0 Kelvin and also describe the qualitative temperature dependence of the Fermi energy. So if we have a particular system and you can calculate the energy states, and then you look at how the energy states are distributed at the energy level, at the energy scale, and that gives you the density of states. So the density of states multiplied by in a particular energy interval will be the total number of states within that energy interval from E to E plus D. And for each of those quantum states, the probability that they will be occupied by electrons, it will be given by the Fermi-Dirac distribution function. The states below the Fermi energy, for the most part, they're going to be filled. The states above the Fermi energy, the probability occupying those states with electrons will be relatively low. Okay, so if you multiply these two together, then you get to the total number of electrons with energy between that energy interval, within that energy interval. And then if you do integrate over all possible energies, you get to the total number of electrons. So essentially, if you know the system, you can calculate the distribution of the states, the density of states, and then you know how many electrons you have. So you just throw all those electrons into that system, then you're going to be, if you have more electrons, you're going to fill to a higher level. That means your Fermi energy will be high. If you have few electrons, then you're only going to be filled the bottom portion of the bands, and that your Fermi energy will be low. So really the only thing that could change here is the Fermi energy. So if you're given the temperature, you should be able to calculate where the Fermi energy is. And that gets to the free electron system. So we have the density of states given by this e to the 1/2 dependence. And then with that, at 0 temperature, you can calculate the Fermi energy as a function of the concentration of electrons, which follow this n to the 2/3 power dependence. And then if you think about the average energy of those electrons, you just do the weighted average, you can get to a 3/5 of the Fermi energy of that system. And now remember, this energy is going to be on the order of several electron volts for typical free electron gases that we have in these metals. And when you go to some finite temperature, the Fermi energy and the average energy will change, but only very slightly, because you see here, this kT over the Fermi energy at 0 temperature, this ratio is typically on the order of like 1% or even less. So the correction due to that temperature dependent term is going to be very, very minimal for both the Fermi energy and also the average energy of the electrons. That gets to the last student learning outcome, That is, with that quantum mechanical system, now we predict that the average kinetic energy is going to be on the order of 100 times higher than what's predicted by the classical physics, which is 3½ kT. And that also gives you about 10 times higher of the electron velocity compared to the result from classical physics. And the other thing is the temperature dependence. With the quantum physics, we know that the average kinetic energy and the average electron velocity are mostly temperature independent. But from classical physics, if the energy is 3½ kT, then both the energy and the velocity will depend on temperature. But now, after we learn quantum mechanics, we know that's not quite correct.